You're listening to the Battery Lab from Rigaku, the show for researchers, developers, and industry leaders looking to stay current and straddle the cutting edge of battery advancement and analysis. Stay tuned for another electric conversation with one of the pioneers charging forward to fuel the future. Let's start the show.
Welcome to the Battery Lab podcast. I'm Tim Brado, the host of the show. In each episode, we will offer insights from industry experts and leading academics about cutting-edge research and advancements in battery technology and manufacturing. This is a place to learn about what's happening in the industry today from a variety of viewpoints, including materials, useful analytical tools, manufacturing techniques, battery performance achievements, emerging cell architectures, and improvements in safety. Each podcast consists of a one-on-one interview with an academic or industry expert with an interesting perspective to share. I hope you will listen, learn, and enjoy. We're here today with Dr. Wang. Dr. Wang is a scientist who specializes in lithium ion batteries, including all solid-state batteries. Dr. Wang is currently employed at Enpower Greentech in Ann Arbor, Michigan as an R&D Manager, where he oversees the development and characterization of solid-state battery materials and complete cells. Dr. Wang has a Ph.D. in single molecule science from the University of Science and Technology of China, where he explored the mechanisms of heterogeneous catalysis and strong correlation on prototypical rutile and anatase single crystals and films via a variety of analytical tools, including X-ray diffraction. Dr. Wang, thanks for joining me today.
Hi, Tim. So thanks for having me on this lovely Thanksgiving Eve.
Yes.
Just call me Yang.
Very good. Very good. Well, welcome, Yang. I appreciate it. Yang, so let's begin today with a discussion about your company, Enpower Greentech. When was this company formed and where is it located?
Yeah, sure. So Enpower Greentech was founded in the year 2012. So the headquarters is at San Jose, California. So at this moment, we are operating at 3 sites. It's US, Japan, and China. So in China, we have a kind of full function. We have the R&D, we have the part line, we have finance, HR, everything there. In Japan, so we already established the R&D lab. So we are building a part line there. So in US, we are now building up an R&D lab. So in the next few years, we are also consider to build a part line.
And that R&D lab is there in Ann Arbor, Michigan, where you're located?
Yeah, sure, of course.
Right. Okay. Excellent. And so, what is your company's primary product, and what's your target market?
Yeah, I think there are 2 types of products here at Enpower Greentech. The first one, we call it a semi-solid-state battery. So where we use the least amount of liquid electrolyte. The second type is the all-solid-state battery. So consider the target markets. So at this moment or current stage, so we are focusing on the aircraft market, where you can think about the drones, eVTOL, HAPS. So in terms of drones, so we are not talking about the drones used for taking pictures, videos. We are talking about a kind of little larger drones. It will deliver the package or be used for the pesticide spraying.
Oh, okay.
The HAPS, the full name of the HAPS is the High Altitude Pseudo Satellite. So it's kind of aircraft. It will continuously fly in the stratosphere. So if there is sunshine shine on the aircraft, it will absorb the solar, generate the energy. It will store in the battery. If this turns dark, so the battery will power the aircraft. The third is the eVTOL, which means the electrical vertical takeoff and landing aircraft. It will be used for the short-term transport for people. So in the midterm, so we want to push to apply our battery to the EV market.
Yeah, interesting. Yeah, there's a lot of talk in the industry these days about EV tolls. I can't wait to ride in one someday. That would be
that's a new market.
That's right. Yeah. That would be a lot of fun. And what's so interesting about battery powered aircraft is the lack of noise. Right, literally the only noise you hear is from the fan blades. But other than that, they're quite quiet. And so, if you imagine a world with a lot more aircraft flying around, at first you might think, "Oh, gee, I don't want all that noise," but then you realize, well, they could be silent, and they wouldn't bother you at all. So it's kind of neat. Yeah. So you talked about your primary product being all solid state batteries, and so can you describe what you mean by that, all solid state, and what is unique about your company and your technology compared to other solid state batteries?
Yeah, so the all solid state battery is a terminology where so all parts inside the cell will be in solid status. It's kind of compared to the traditional lithium ion battery, where there will be the liquid electrolyte be used. So because the liquid is organic flammable, it's will cause some safety issue. That's why the one reason why people are pursuing this all solid state battery. So in terms of the specialty of the company, so I would say there are maybe 3 points. The first is about the leader of the company. So our CEO is Dr. Sam Dai, so who got a doctorate degree in Professor John Goodenough's lab at UT Austin. So our CTO is Dr. Che Yung. So he got his doctorate degree at the Tokyo Institute of Technology. Mm-hmm. So after graduate, so he has been staying in the battery field for more than 20 years. So we also have the expert in the R&D side who has more than 30 years experience in the battery field. In the meantime, we also have the expert in the industrialization area. He has more than 40 years experience, so which means we are kind of strength or emphasize both the R&D and the industrialization directions. So the second part is the collaboration. So we have this long collaboration with the world leading scientists. So one is Professor John Goodenough's from UT Austin. Mm-hmm. So he is the leading scientist in the cathode materials. Second one is the Professor Kana Rajo is from Tokyo Institute of Technology. So he is the leading scientist in the solid state electrolyte. The third one is the Professor Achu Yamada from Tokyo University. So he is the leading scientist on the liquid electrolyte. So the third point and the most important point is our technology. So Enpower Greentech is characterized as a solid-state battery. So here we have a clear roadmap to how to realize the all solid-state battery. Because all solid-state battery is very challenging at this moment. So at this moment, so we are emphasized on this semi-solid-state battery, try to commercialize it. In the meantime, we also emphasize on the R&D of this all solid-state battery. So in the semi-solid-state battery, so our kind of core technology is we know how to optimize the electrolyte. It can have a better interface between the separator and the electrolyte, and also between the electrolyte and the anode. So by doing so, we can kind of push the energy density to very high, but in the meantime, we wouldn't compromise a lot of the cycle life and the power of the battery. And also, so we have some special design for the organic electrolyte, so it wouldn't catch fire. So recently, there's third-party tests so show our pouch cell can pass through the needle penetration test, so there will be no fire. Mm-hmm. So in terms of the all solid-state battery, so we are using the sulfide-based electrolyte. So we have this patent license. We can manufacture and sell this LGPS electrolyte. We are also in R&D side. We are also trying to how to use this LGPS electrolyte to scale up the capacity of the all solid state battery.
Okay, interesting. Sulfide-based electrolyte, and you said LGPS.
LGPS, which means so inside it contains lithium, germanium, phosphor, and sulfur.
Mm-hmm. Interesting. And then traditional cathode type materials, is that what you tend to use? Like an NMC type cathode, or do you use a variety of different materials?
So our main focus is on the NCM 811. It has a high nickel compound and the least amount of cobalt at this moment.
Right.
Yeah.
And the high nickel content provides much higher energy density, at least on the first charge. Some of the challenges in the industry with high nickel content cathodes is that gain that you get initially in capacity tends to fade more quickly with high nickel content. So then there's more doping and advancements in layered cathodes and everything to try to resolve some of those issues. So I'm sure you're busy working on resolving some of those challenges.
That's correct.
And so are these solid state batteries that your company, Enpower Greentech, are they currently available to customers?
I would say some of them. So for the semi-solid state battery, so currently we already developed the pouch cells with the capacity between 3 to 24 amp hour to the aircraft customers. So actually, so in this year, so we announced the news. We already pushed the capacity of the pouch cell to above 100 amp hour. In the meantime, we also pushed the cylindrical cell. It is the 18650 one to push the capacity to 4.1 amp hour. So we are trying to industrialization of these these two type cells, hopefully, so they can be delivered to the customer in the next 2 years. So in terms of the all solid state battery, I have to admit it's very challenging to industrialization. Mm-hmm. So our goal is in the next 5 years, we will try to deliver it to the customer.
That's very impressive. A 100 amp hour pouch cell battery. Yes. For those in the audience that might not be familiar with some of those numbers, a large lead acid battery that you might see in an RV or an electric trolling motor in a boat, a deep cycle marine type battery is usually about 120 amp hours, and it weighs about 60 to 70 pounds. And you're talking about putting 100 amp hours into a pouch cell. So let's shift gears a little bit and look at the overall battery industry. What challenges exist today with similar all solid state batteries, in terms of supply chain, performance, lifetime, manufacturability? I mean, every battery technology has its challenges. And it sounds like your company's doing a great job of overcoming those challenges, but the industry at large tends to struggle with some of these issues when it comes to either conventional lithium ion batteries or even solid state batteries. There's always some sort of issue when it comes to trying to improve performance or improve lifetime or getting the raw materials from a supply chain standpoint. So what do you see as some of the primary challenges in the industry for all solid state batteries in general?
Yeah, I think that's a good point. So in considering the supply chain and the manufacturability, because at this moment there is a kind of no uniform of the technology of this electrolyte, right? So, for example, so if the company want to commercialize or industrialization, probably so the best way is they need to build up their own manufacturing factory. This kind of, they have to secure the raw material. They have to have the money or fund to build this manufacturing. Yeah, this would be challenging in terms of the supply chain or the manufacturing. So in terms of the performance, I would say it should be more specific to discuss these things, because generally, so you can divide this all solid state battery depends on what types of electrolyte they will use. So like the Enpower Greentech, so we use the sulfide based electrolyte, right? Mm-hmm. I know there are also companies Then we will use the oxide-based electrolyte, and some will use polymer-based electrolyte, right? Different types of electrolyte will have different issues. For example, the sulfide-based electrolyte, right? So the sulfide is not stable in air. So in order to use this, you need to kind of set up an environment to protect the sulfide during the process of manufacturing. This is the challenge for this one. Mm-hmm. For the oxide-based electrolyte, so it's robust, but it's also brittle, right? So maybe it's easier to build a cell with few layers, but if you go to multi-layers or even 100 layers, it's kind of challenge. Yeah, that is one thing that people is working on, the oxide-based one. In terms of the polymer-based electrolyte, yeah, so the main issue is it has the low analytical conductivity. So even at room temperature, not even talk about a low temperature, right? So the fast charge or discharge will be an issue for this polymer-based electrolyte.
Mm-hmm. Mm-hmm. Yeah, I mean that's always a challenge for battery technology. That batteries are very temperature sensitive, especially depending on what type of electrolyte you're using, right? So if you're using something like a lithium fluorophosphate, hexafluorophosphate, that is less sensitive to temperature. But things like polymer-based electrolytes, right? Even room temperature can be fairly poor performance. Yes. Freezing temperatures can literally double or triple the internal impedance of the cell, and it just can't deliver current anymore. It can't deliver power, and so they've been working on that for years to try to improve that ionic conductivity of polymer-based electrolytes. And it's interesting that you're working on these sulfide-based, which, as I understand it, the sulfide-based electrolytes are not brittle, but they're also not as pliable as the polymer, right? They're a little bit in between. They're sort of a semi-solid, kind of a densified kind of material.
Soft, like a clay or dough.
Mm-hmm. Right.
Yeah.
And that
they have the good side of it, right? It's easy to handle and to integrate inside the battery.
Right. All right. So if we were to look at just looking out a little bit into the future here, obviously, right now we're working with a bunch of known materials, and we still have ideas on ongoing efforts of building and proving certain technologies, and then we have ideas in the future of even other technologies that could be pursued, but maybe aren't pursuing them much as an industry just yet. But if we look at today's solid-state batteries, not your company, but just in general across the industry, solid-state battery chemistry. What performance improvements do you expect to see in the next few years, and why? And so I'm not talking about new novel materials. I'm talking materials that are already in development and working towards production. But it'll be a few years yet. But when they do come to production, what do you expect to see in terms of how will they perform differently than the solid-state batteries that are in production today?
Yeah, sure. I think there are several points. The first is would say is the energy density, because theoretically, so the energy density of this all solid-state battery can be super high, maybe larger than 500 watt-hour per kilogram, but realistically, so they are not that high at this moment. So maybe they're kind of slightly higher than the traditional lithium-ion battery, but still, so there is a big gap right between the realistic and the theoretical. So I think so the one direction is still people need to kind of push the energy density of this all solid-state battery to even higher and higher. Yeah. The second is the cycling life, because some certain type of oxide, some certain type of electrolyte, so the cycling life is not that high, because for the traditional lithium-ion battery, so they can even achieve 1,000 cycle life without the capacity dropping too much. So, but for the solid-state battery, so usually it's not that easy to reach 1,000 cycles. But if you want to apply this solid-state battery in the EV market, I think this is one direction that people should kind of working very hard on. The third one is the external pressure. So at this moment, so in order to have a good performance, most of the step battery you need to apply very high external pressure to kind of keep everything sticky and the uniform cycling. So which means people usually will use the additional tools or clamps to apply this external pressure, but it's not good, right? So maybe if for one cell, two cell, it's very easy to apply this external pressure, right? But consider so the UV, right? There's hundreds of cells there, right? It's not easy to apply this external pressure. Yeah, people need to think about either how to easily to apply this external pressure, or maybe there's no need for external pressure applied in the future.
Okay. Yeah, that's well, I mean, I've been hearing about some other solid state chemistries that don't require external pressure, but traditionally, yes, that's been one of the challenges because there's no liquid to sort of soak in between the electrodes. So it's hard to get a good conductivity path for the lithium ions to flow. And so by applying pressure, you get those materials in closer contact and get that better conductivity, the better interface. So interesting to see where that goes.
This is one reason. Another reason is because in this solid state battery, that people always we wouldn't use the traditional graphite as anode.
Mm-hmm.
They will use either silicon or lithium metal anode, or even some people will claim there is anode free. So under this type of anode, so the volume will change very large, obviously, right? So the volume change is not a good thing for battery. That's why people also need to use this pressure kind of decrease the volume change during cycling.
Right. Well, because studies have shown that without pressure, as the volume changes in the anode, lithium migrates from the cathode into the anode upon charge. Not only does the anode swell and grow in size volumetrically, but dendrites are formed, and then on discharge, that lithium goes back to the cathode. However, it creates voids. It leaves voids on that interface with the electrolyte, and studies have shown that if you apply pressure, it helps to minimize those voids and helps to minimize the growth of dendrites. So to come up with a technology that can accomplish the same thing without the external pressure, that would be ideal, because the external pressure, to your point, really complicates the end application design, right? So you can obviously design an R&D battery where you just apply pressure and everything works great, but then how do you put that into an application and apply external pressure to an entire battery pack or series of battery packs inside of a car or an aircraft? And that's a challenge. So, okay, but speaking of, you had mentioned electric vehicles as, another good market for solid state batteries, but it's also a great market today for traditional lithium ion batteries. In fact, it's the largest and most demanding market for batteries in the world. Within the EV market, virtually every performance metric for a battery is being pushed to the limits, much like in the aircraft type application space that your company is targeting. The only certain battery chemistries are even capable of meeting these challenging requirements. Today, the EV industry uses traditional lithium ion batteries with liquid electrolytes and varying electrode materials to optimize their performance, the energy density, and the cost. What challenges do you see with these existing lithium ion production scale batteries, and how can they be mitigated with a future transition to all solid state batteries?
Okay, yeah, sure. So I would say the first thing is most concerned to the customers is the safety issue, because we know for the traditional lithium ion, so people will use the organic electrolyte there, right? This organic is quite flammable, so usually during an accident, so if the battery is catching fire, so actually there's nothing you can do, just sit here wait for the battery totally burn out.
Right.
This is not good, right? It will cause a lot of damage to the cars or even to the driver, the passenger there, right? Mm-hmm.
So safety,
yeah, so
safety big issue,
yeah,
right?
safety.
Okay.
Yeah. So the all solid state battery is quite fit to solve this problem because so everything inside the solid state battery is a solid state, right? So none of them is flammable, right? So during the accident, even the cell break, even there is a shortage, there wouldn't be catch fire. So that's a very good thing. The second thing is kind of, people usually call it the range of charge anxiety, right? So at this moment, so generally, so for EV cars, one charge will only last 300 miles. So yeah, if you buy a more expensive one, it will last for 400 miles, right? So people are kind of eager to want to have a car. During one charge, it can at least last for 600 miles, right?
Right.
Yeah. So for this all solid state battery, so people will use the next generation materials in terms of cathode or the anode. Yeah, cathode people will pursue the NCM 811. It's a very high nickel content, right? It kind of give a high specific capacity. In the anode side, that is a big improvement. So people will use the silicon or use the lithium as anode. So compared to the traditional graphite, so the silicon or the lithium is kind of have 10 times as large as the capacity, specific capacity, which means, right, so if you use the same weight of the anode, so the lithium anode or silicon anode will give you a higher energy density, which means, so yeah, it will give you a higher range, right? If you put this kind of batteries in the cars.
Right. So did I hear you correctly? It was like a 10 times improvement between traditional graphite and silicon-based anode?
Not 10 times.
Not 10 times.
10 times means the specific capacity is 10 times.
Yes.
But if you integrate this one into the battery, you need to also consider the weight contribution from the cathode and electrolyte.
Mm-hmm.
So probably it's 1.5 times or 2 times larger. Yeah.
Okay.
Yeah.
But it's significant. That's not just an incremental improvement. That's a real, measurable, quantifiable improvement that people would actually notice in their car to suddenly have, so much more, 20% more range, right? Or 50% more range out of a battery. So excellent. Any other thoughts there?
Yes. Yeah, the third one I would say is a low temperature performance, right? So because currently it's traditional lithium ion battery, so they use the organic liquid electrolyte.
Mm-hmm.
So if the temperature dropped and the analytical conductivity will drops exponentially, that's one thing. Another thing is if temperature drops, though the electrolyte will become very sticky, so it's not good for the lithium ion transfer. So that's why it will have the low temperature performance issues. So if people turn to the solid state electrolyte, so the temperature dependence of the analytical conductivity is not that significant. So still, I would imagine, so the battery will give a good performance even at a low temperature.
Interesting. So you're saying that this, like a sulfide-based type electrolyte is
yes. So generally speaking, so the sulfide-based or most of the sulfide-based electrolyte will give very high ionic conductivity. But recently, there are a few of oxide-based electrolyte will also give very high ionic conductivity.
Okay, and you're saying that those solid electrolytes, those two types of solid electrolytes, are actually less temperature sensitive than traditional LiPF6. Lithium hexafluorophosphate. Okay, interesting. Mm-hmm. Yeah. All right. So it sounds interesting and intriguing that there are improvements to be made in the battery space. Today we use traditional lithium-ion batteries in electric vehicles, and now you're saying there are solid-state batteries that can do all that and more, improve the performance, improve the range, improve the speed of charge and things like that. So then how likely do you see that happening, the adoption by the EV industry to adopt all solid state batteries. Is that something that you think is just around the corner? Is there going to be announcements within the next few years of major automobile manufacturers deploying solid state batteries, or do you think there's still some challenges to be resolved and be a few more years until that happens?
Yeah, so I think different people will have a different opinion. So for me, I'm maybe more kind of conservative, I would say. Yeah, so I don't expect that it can happen quite soon, or maybe quite soon, which means in the next 3 or 5 years, because I can see, for the industrialization, because I can see there are some issues. Mm-hmm. The first is the scaling up. In terms of the scaling up of the cell capacity, mm-hmm. also scaling up of the manufacturing. So in terms of the cell capacity, so far I would see in the market, so the capacity of this all solid state battery maybe just around 20, 30, or 50 amp hour. But in order to really apply this all solid state battery into the EV cars, so I would expect the capacity should be around 100 ampere hour. This is very challenging. So when you increase the capacity, the difficulty is not just increase linearly. It may sometimes increase exponentially. Yeah. The second is the manufacturing, because so this electrolyte is very special, right? So it's not easy to quickly to build up a factory and secure the raw materials and quickly to get the slide come out. And also it's not easy to massively produce the batteries. Also, it's also related to the second point is the cost per cell or the cost per watt hour. Because the EV market is kind of very cost sensitive if you compare to the consumer market or the aircraft market, right? So which means the customers always want to have the batteries have the highest performance but lowest cost, right?
Right.
But so in order to achieve this, so from the perspective of the cell manufacturers, so they kind of have to quickly scale up. They kind of have to secure a lot of demands from the EV vendors, right? It is also typically it's not that easy. Yeah.
Okay. Well, that's interesting. I'd like to now talk about not the technology per se, but how to analyze the technology. How do you, as a scientist and like in your role as an R&D manager, how do you evaluate and characterize these different battery chemistries? So can you talk a little bit about what kind of material analysis is currently used for all solid state batteries to evaluate the quality and consistency of these electrode materials?
Yeah, sure. So first, I would say the material characterization is very important or very critical for the process control and the failure analysis, right? So generally, there are general analyses for the electrolyte and electrodes. So it's in terms of the thickness, surface roughness, porosity, particle size. Yeah, this kind of properties can be characterized by the SEM, AFM, confocal microscope, right? So of course, there are also spatial characterizations for each component. For example, for the cathode or oxide electrolyte or silicon-related anode, so there are the crystallized powder inside, right? So in order to characterize the crystallinity, the people will use the XRD or the Raman spectroscopy. Of course, sometimes people also are interested in the chemical composition or even the oxidation status of the materials. So at this moment, so the XPS, SPOES, SPMS can be considered. So the last thing, so I realized, the cryo TM is kind of more popular, be used inside the battery field. So because the TM will operate in a very low temperature, so the high energy beam from the column will not cause a lot of damage. So it will be a very powerful tool to study the structure and the chemical scene inside the SEI layers. But of course, so the sample preparation and the equipment operation of this cryo TM is, I would say, quite elegant.
Mm-hmm. And so, I mean, that you just mentioned a lot of different types of analytical methods and tools. So how does that really compare then? How would you analyze the difference between or what would the analytical tools be different between a liquid electrolyte battery and an all solid state battery? Are there differences? Do you use different tools and techniques, or is it pretty much the same types of tools and techniques?
So I would say that the technical is kind of most of the same, but maybe the sample preparation maybe would be a little different. Because for the liquid electrolyte, if you use liquid electrolyte, right, so the batteries is kind of very easy to separate each component, which means you open the cell, you can easily to isolate the cathode, separator, anode. You can study them individually or one by one, right? Mm-hmm. So, but in terms of the all solid state battery, so because of the cycling and high pressure you applied, right? So if you want to do a post-mortem, it's kind of hard to separate each component. You have to characterize them together. But of course, there are ways you can go to different layers, use different technologies. Maybe there's one thing is different is called the in situ characterization, because the all solid state battery, right, there is no liquid inside, so which makes it easier to use some vacuum related techniques to do the in situ characterization. Because, for example, you can directly put the cells inside the SEM, because it works in a vacuum environment, right? You just directly put it inside, characterize either the surface change or the cross section change, or you can easily put it inside put the all solid state battery in the XPS chamber to check the composition or oxidation status change, right? But you couldn't directly put the solid liquid electrolyte battery inside because there is a liquid, so it will evaporate inside the chamber.
Right.
Yeah.
Yeah, there's a lot of challenges when, like you said, when it comes to sample prep. How do you isolate the material, and how do you get it into the chamber? And then, if the sample is air sensitive, you can't really just put it into a ambient air chamber and expect to get good test results, because it's literally oxidizing and changing before your eyes while you're trying to analyze it. So, so those are challenges. Certain types of analytical tools are under vacuum or under a gas environment. Others are not. And so, so others are free air, ambient air environments. And so if you've got a particularly air sensitive material, that makes it difficult. And so now the industry the analytical tool industry has to make some changes to maybe catch up to some of the needs of the battery industry, because you're dealing with such easily oxidizing type materials and moisture sensitive materials that it's critical to have more elaborate type analytical tools in order to make your life easier as a researcher.
Yeah.
Now, what trends do you see then in the rechargeable battery industry? And I'm not talking about necessarily any technology, just rechargeable batteries in general. What are some of the most exciting materials or architecture changes that you're seeing in the industry?
Yeah. Okay. So I think so far we talked about the battery design and the performance, right? Mm-hmm. So I think we can kind of zoom out a little bit, right, to look at the whole supply chain and the things of this battery, right? So I can see there are kind of two trends or two techniques make me feeling excited. The first one is the dry process. So
dry process. Okay, for the like the cathode.
Yeah. So it's kind of compare the traditional way how you prepare the cathode and the anode, right? So for the traditional way, you need to kind of use the organic solvent to mix the materials, binders, conductors together, do the slurry coating, and then dry them at a very at a elevated temperature, right? The whole process is first is complicated. Second is kind of energy consuming, right? So the dry process is we say it's a better technology. So it just use innovative way to mix the materials and do the coating, and that's it, right? The process is simple, and the energy consuming is quite low compared to the traditional way. So people already use this dry process for the cathode. So I'm also seeing people is trying to use this dry process for the separator and anode side. It's a very good thing. A second technical, I would say, is called the direct lithium extraction, right? It's kind of in the very upstream of the supply, right? So in order to get lithium or lithium-related compound, so the traditional way is just people will pump the brine out and put this brine in a lot of ponds, let the sun to evaporate it. So the whole process will take a super long time. So there are the new techniques. They can directly extract or concentrate the lithium from this brine water. It is very quick. The reason of this technique is exciting because the demand of lithium or lithium-related compounds is growing very fast. Although the storage of the lithium or lithium-related compounds is very abundant in the earth, right? Actually, the mining time is super long. So I would say the mining speed couldn't catch up with the demanded speed, right? There should be some new technique that can directly extract or concentrate the lithium from this brine water. Yeah, that's two techniques.
Okay,
which makes me feel exciting.
Yeah, no, that's interesting because, as you mentioned, I mean, we think we have supply chain problems today. wait till automotive manufacturers start to ramp up EV battery production, and they're literally consuming all of the world's available lithium mining resources. And then the demand is going to still be way beyond those available resources. So there will be definitely some choke points and some supply chain issues as we try to move towards more electrification with battery power and using lithium ion batteries, and especially if we start going to lithium metal anodes, that it's going to be some cost challenges there as the demand starts to push up the price of the available lithium. So that's why the industry is really working hard to still consider other technologies, right? Looking at sodium ion and magnesium ion and other types of batteries and zinc-based chemistries, trying to get away from lithium, not because lithium isn't good, but because there's only so much lithium and not necessarily enough to go around. And it's not easy to mine. But as you pointed out, it could become easier with this direct lithium extraction methodology. Yes. But it's going to take technology improvements at every level, not just battery technology, but to your point, extraction technologies, manufacturing technologies, right? So, interesting. So I just have one last question for you, Dr. Wang. Do you have thoughts about the future of the battery industry and where we might be in 10 plus years? For example, we'll see significant battery performance improvement after the current wave of advanced materials are explored. At least I think we will. Maybe you see it different, but that's what I'm looking for is your opinion on this. But, will we see significant battery performance? I guess is the right way to ask that question. Or do you think we're already seeing the limits of available battery chemistries and are limited to incremental improvements going forward?
Yeah, I would agree with you. There will be more and more the market saturation come out. Because so for the new technology, it couldn't push every metrics of the battery, right? So which means you for next year at least at this moment you couldn't have a battery. It has the high energy density, high power, and long cycle life, right? Like things. So you need to kind of customize the battery to a different market, right? So for example, the aircraft market, they emphasize on the energy density, right? So for the EV market, they emphasize on the safety and the cycle life, right? So I would expect in the future, so there'll be more and more companies come out. Will have this kind of market specialized or customerized, right, products. It depends on what kind of products they will or market they will deliver their products. The second part, yes. So I would say there will be the limitation of the chemistry, because I can see still the people is try to find the new materials in the cathode or in the anode to try to increase with the high specific capacity, right? For example, one direction is the lithium sulfur battery, right? Theoretically, it can give the energy density higher than 600 watt-hour per kilogram, but it's a challenge. But still, yeah, we know there will be and there should be some new materials. It will give you a high specific capacity. So, and thus will give you a high energy density if you use this material inside the batteries. Just the people, the scientists or the engineer need to keep working very hard to do this job.
Right.
Yeah.
Okay, well, I think that's going to be the final word for this episode. So thank you so much, Dr. Wang. I appreciate it. That was a lot of fun and very interesting. I know I learned a lot. I hope our audience enjoyed the discussion. And to our listeners, thanks for joining today. We hope the discussion has been informative and valuable to you. Please make sure to come back and tune in to another episode of The Battery Lab.
We all want a more reliable, safe, and efficient future. That's why here at Rigaku, we're helping to power tomorrow through advanced analytical technology for battery research and quality control. We offer proven material analysis, identification, and quantitation to ensure you can develop battery products in confidence. Find out more at battery.rigaku.com. You've been listening to The Battery Lab. Make sure you never miss an episode by following the show on your favorite podcast player. Please give us a rating, leave a comment, and share the episodes you love. That helps us power more electrifying conversations and helps keep you current on the latest battery research. We hope to see you again, charged and ready, next time.